You know, if every triangle were a right triangle, life would be, I guess, a little bit boring, but it would certainly be easy to deal with because we'd have the Pythagorean theorem holding for every single triangle if all triangles were right. But as you know, not all triangles are right. Here's a wrong triangle. So not every triangle has an angle that has 90 degrees. So what do? Well, it turns out there's a wonderful law that actually generalizes the Pythagorean theorem, which actually now will hold for every single triangle you can think of, even the ones that aren't right. So now we're going to generalize the Pythagorean theorem. Really cool. This is called the law of cosines. Let's check it out together. So the law of cosines says if you take any triangle at all, it doesn't have to be right anymore, so A, B, C, and the sides are labeled accordingly, so lowercase, opposite to the angle, so A angle has side opposite little a, B angle has side opposite little b, and so forth. Then it turns out that you have these three identities. Let's just take a look at the first identity. In fact, I don't want you to look at too many of them because they look sort of intimidating at first. So just don't be intimidated. Let's just cover that up. Do you see it looks like the Pythagorean theorem? Right? Leg squared plus leg squared equals hypotenuse squared. Well, there's no hypotenuse, there's no leg, this is the generic triangle. So instead we have to be a little bit careful, and to make this thing hold, what we see is that if you pick a particular angle, like pick A as an angle, that's my angle, then what I see is that if I think of this kind of as the, quote, hypotenuse, it's really not, but just think of this that way, then that squared will equal this squared plus that squared, but since it's not a right triangle, it's not correct, I've got to subtract off something. I subtract off 2 times the product of these lengths that straddle the angle multiplied by the cosine of the angle itself. That's why it's called the law of cosines, because the cosine appears there. It's a very weird looking thing, but let me say it again. If you pick this angle as the sort of angle that you care about, then the opposite side squared will equal the sum of the squares of the flanking sides minus 2 times the product of the lengths of the flanking sides times the cosine of that angle. Wow. Now, the reason why I've got 3 copies of it is because this actually holds no matter which angle you pick. For example, if you pick B as your angle, well then you've got B squared equals the sum of the squares of the flanking sides, A squared plus C squared, minus 2 times the product of these lengths, AC, times the cosine of B. You see how now the B is replaced by the A in the previous one? Let's do the C one. If we do the C one, what should we see? We should see that C squared will equal the flanking side squared, A squared plus B squared, minus 2 times AB cosine C. C squared equals A squared plus B squared minus 2AB cosine C, just like we guessed. That is the law of cosines, and it actually is the generalization of the Pythagorean theorem. So if you said, boy, I wish that the Pythagorean theorem holds for every single triangle, even my favorite one, it does, as long as you use the law of cosines. That's the right generalization. Let's take a look at some examples, and you can see the power of this wonderful law. So here is a little triangle. We know this angle is 49 degrees. We know that this side is 11. We know that this side is 12. I want to figure out this side. Now, you can imagine a friend saying, hey, wait a minute, just use Pythagorean theorem. But you can't, because this is not necessarily a right triangle. But we can use the generalization, the law of cosines, and that holds for all triangles. So what am I going to do? I'm going to have to pick my angle. Well, I'm going to pick my angle to be y, and I'm going to want this side here, which I'm going to call, I guess, little y. And so what do I know? Well, I use the formula that says that little y squared is going to equal the sum of the squares of the flanking sides, 11 squared plus 12 squared, minus 2 times 11 times 12, that's the product of the flanking sides, times the cosine of what? Well, of 49 degrees. A long thing to write down, but the payoff is huge. You're going to find out this length. So we can simplify this a little bit, I guess. This is 121 plus 144 minus, this product here is 264 cosine of 49 degrees. And so this equals 265 minus 264 cosine of 49 degrees. And now I'm going to actually sort of poop out here and say, okay, let's now just approximate this on a calculator. I see 91.8 That's the y squared, and so I take square roots, and this is a length, so it's positive square root. So this tells me that if I take the square root, hit the square root key, I'd see, if I round, approximately 9.6. So this length is 9.6, and I was able to find that using the law of cosines. Neat. Let's try one more example. Here we go. One more. I know you want more, but you're only going to get this one. I'm cutting you off from the law of cosines. All right, so here is a triangle. We're given all the sides, and I want to find out this angle right here, this angle Q. How am I going to do that? I'm going to use the law of cosines with that as my special angle. So what does that mean? It means that this squared is going to equal this squared plus that squared minus 2 times this product times the cosine of the mysterious angle. So I see that 7 squared will equal 5 squared, the flanking side, plus the other flanking side, squared, minus 2 times the product of those flanking sides, 5 times 10, times the cosine of Q. And you see why I like that? Because I got Q in the picture. I have a relationship that links Q to all these constant numbers. I can now actually solve for Q. So let's do that. I see 49 equals 125 minus, and this is 100, cosine Q. And so if I subtract 125 from both sides, I see, well, actually, okay. So let's do that. I see negative 76, subtracting 125 from both sides, equals negative 100 cosine Q. And if I divide both sides by negative 100, then on the left-hand side, a negative divided by a negative is a positive, and I just see 0.76. And so I see that the cosine of Q equals 0.76. Well, what's Q? Well, it's the inverse of cosine. And so what do I have? I see that Q equals the inverse cosine of 0.76, right? Q is the angle whose cosine is 0.76. I can use a calculator now, and if I round, this rounds out to be about 41 degrees. So I see that this angle is 41 degrees. Notice I was able to do that using the law of cosines. This is actually fantastic. The law of cosines is a wonderful way to extend the Pythagorean theorem to any triangle at all. Neat.